So I'm here in the library of the European Southern Observatory's Chile headquarters in Santiago. It's a little bit of a cloudy midsummer day or early summer day, and I've been having a fascinating discussion with a postdoctoral fellow here who is actually from France, Michael Marsset, and he's specializing in the study of early solar system bodies, early asteroids, which range from meters to, I believe, Mikhail, what was the largest size that you had? What is the range of the bodies that you were studying?
Yeah, so from meter-sized objects to a few hundred kilometers. So the largest object, for instance, in the asteroid belt is Ceres, which is 900 kilometers in size.
Which is now considered a dwarf planet. And you were very interested in the earliest formation of these asteroids and the identification of meteorites on Earth that correlate to populations of these small bodies in the main asteroid belt.
Exactly. So small bodies in our solar system, they tell us the story of the early protoplanetary disk in which the Earth and other planets in our solar system formed and evolved over time. So the chemical and isotopic composition of meteorites that we find on Earth is our main source of information about our early solar system. And we can link these objects that we can study in laboratories to objects that we see in the sky through astronomical observations. And also the astronomical observation of small bodies teach us about their compositional distribution, and their compositional distribution depends on how giant planets migrated early in our solar system. So where we find small bodies in our solar system today and where we don't find them tell us the story about how planets formed and evolved in 4.5 billion years ago in the early young solar system.
And you were telling me that this research is being aided greatly by the advance of technology, specifically with an instrument on the ESO Very Large Telescope at Paranal Observatory in northern Chile in the Atacama Desert. I actually was privileged enough to visit during its construction back in '99, a long time ago, and it's all four UTs are being used at the moment with new technology, which wasn't even there when I was there. And one of the instruments that you use currently is SPHERE. Can you tell us what that stands for and how you're using it?
I'm sorry, I can't remember what what it means exactly, but it's an instrument that was developed to image exoplanet and protoplanetary disks around other stars. But our team, so with my collaborators in France, like Pierre Vernazza from ex-Marsset University, and other people in France and Czech Republic, we decided to use this instrument to get accurate images of asteroids. So how do we know the composition of asteroids? Usually we do that through with powerful spectrograph, but this gives you the surface composition of the object, because it tells you how the light from the sun is reflected at the surface of the asteroid, and that's a proxy for surface composition. What we can do with SPHERE is get accurate images of these objects, and we can study their shape, their geology, and by knowing the shape and the size and the volume, we can understand their density, their bulk density. And so combined with spectroscopic information of their surface, we can tell, okay, we have this surface composition, but we see a very high density, so it means that the interior must be differentiated. Or on the contrary, if the density we measure is compatible with what we see at the surface, then we know it's an object that is compositionally homogeneous. So thanks to this instrument, SPHERE, and the very accurate images it allows to take of asteroids, we can better understand their geological evolution and whether this object stays as homogeneous objects, or if they differentiated into a nucleus, a mantle, and a crust, just like the Earth did.
And what is the future of this research in the next 3 to 5 years? I mean, what are you going to be focusing on?
Yeah, so at the moment I'm focusing on understanding the topography of the largest asteroid in the main belt. Objects like Sirius and Vesta, but Sirius and Vesta we know them pretty well because they were visited by spacecrafts. But the third largest object in the asteroid belt called Pallas, which historically was the second object to be discovered in the asteroid belt, this one is much more mysterious because it wasn't visited by a spacecraft. And so by studying its topography, thanks to our images taken with here, we try to understand if the crust or the subsurface is dry or if it comprises some water ice. And I had a student this year, Julie Vermersch, who is a geophysicist and who's been working on this problem with me during the year. So based on the topography of Pallas, we try to understand if this type of objects is water rich, and if this type of object could have contributed to bringing water to the early Earth.
And to my knowledge, Pallas there's never even been a flyby of Pallas, has there? It's never been visited or orbited by a spacecraft.
That's correct, yes.
So maybe ESA and NASA will get together and hopefully send a flyby mission to Pallas soon, or maybe better yet, an orbiter. But Pallas, if I'm not incorrect, it's not exactly coplanar. Is that right? It's a little bit inclined to the rest of the solar system?
That's correct. It's on a very inclined orbit, and so it's not very easy to reach for a spacecraft because it's not in the plane of orbits of the Earth and most planets and planetesimal in our solar system.
So it requires more fuel and much more rocket science, so to speak.
Yes.
Well, anyway, Mikhail, thank you so much for your time today. Appreciate it, and good luck with your future research.
Thank you very much.